So now we have gone through the work of finding the area under a function under certain conditions over a closed interval by using approximating rectangles for a finite number of rectangles. The name we have for that sum of the areas of those rectangles is a Riemann sum. The Riemann sum represents the area under the curve bounded below by the x-axis as long as the function f is greater than 0. That is so that we can interpret these products here. F of xi star would be the height of the rectangle and delta x would be its width. The product of the height and the width we can interpret geometrically as an area. However, more generally speaking, the function f might go below the x-axis where the outputs of f would be negative, and then this product would be a negative quantity. Rather than having us interpret that negative quantity also as an area, because that does not make geometric sense, we instead would interpret it as finding the difference in areas from the areas above the x-axis versus the areas below the x-axis. We would take the difference in those. And we should take a look at an interpretation here of that geometric area with respect to distance, which is what we looked at also as an interpretation for what we're doing here. Section 5.2 is our formal introduction to what is called the definite integral in calculus. Right? So the notation we're going to discuss in this section is this notation here. We have this is the integral symbol right here. It is an elongated S, and it is interpreted as meaning summation, but not just a summation like this summation symbol here. In fact, that elongated S means we're taking the limit as n goes to infinity of this summation. By analogy, this is similar to the notation we use for the differential operator, such as the prime notation or the Leibniz notation, something like d over dx. That notation as well represented the limit of some operation that we had applied. So this is the integral operator. It means that we are taking a summation of an infinite amount, an uncountable number of, in this case, geometric areas, and with the Riemann sum, we're interpreting those areas specifically as rectangles. The a and the b, we have, or you can call it a lower bound and an upper bound for the integration. This is indicating that we are on the interval, the closed interval from a to b. We'll take a look at this geometrically again so we can match this up symbolically with its geometric interpretation. F of x is the function which would need to be integrable on the closed interval from a to b, and dx is the differential. And the differential indicates to us symbolically which variable that the function is going to be integrated with respect to. And this is a single variable function, f of x, so the only differential we see here is a dx. When you're in a future course, if you're dealing with multivariable functions, if we had more than one input variable, let's say we had z as a function of x and y, for instance, then if we were to integrate, we'd be integrating over an area with both x and y components. And so we would have to have more than one differential here and in the appropriate order of the integration to be applied. So here's an introduction to the notation of the definite integral and our interpretation of what the definite integral is. It is the limit as n goes to infinity of a Riemann sum. And again, the Riemann sum is the name that we have for when we are taking the sum of a finite number of rectangular areas. So in this section, we're going to be evaluating and interpreting the definite integrals. We'll be able to do that geometrically by graphing the function f and the closed interval from a to b, and let's say shading in the regions of the curve that are bounded also by the x-axis, and then evaluating the integral as the sum or the difference of the geometric areas that we find. Interpretation, let's take a look at another velocity function where we want to evaluate the integral in order to have a decent interpretation for what we're actually reading from the graph when we find one of these integrals. And we recall that when we did areas and distances, finding areas under the curve, we could choose our xi star value to be any x value within each of the subintervals that we had selected from after subdividing the closed interval a to b. And one of the choices that we focused on, of the three choices that we looked at, we had left endpoint rule, we had right endpoint rule, and we had midpoint as well. So the midpoint rule in this section, the midpoint rule specifically addresses finding the approximate value of a definite integral by using a finite number of rectangles in a Riemann sum, okay, where we are choosing the xi star value to specifically be the midpoint of each subinterval. Okay, let's get into the geometry of this right now. And this delta x right here, again, delta x equals b minus a over n is the formula we're typically going to be using. We're dealing here in this section with functions that are going to be continuous, and we're going to be able to express them symbolically as well when we are constructing the symbolic integral and evaluating the symbolic integral as well. In that case, since we have continuity, we can choose delta x to be on a uniform partition. Okay, so we can partition the closed interval from a to b uniformly, so that the width of each subinterval can be calculated as b minus a over n, where n is again the number of rectangles, the number of subintervals, and hence the number of rectangles. So here was an example of the graph of a function we were looking at in the previous section. Notice from here that f happens to be a function that is specifically greater than 0. Okay, it's specifically greater than 0, okay, on the closed interval a to b. And as such, if we were to find this region A, okay, A is interpreted as the area of this shape. Okay, it's the area of that region. Okay. And when we do the Riemann sum for this, okay, if we calculate a Riemann sum, that's where we're taking a finite number of rectangles, is the Riemann sum. Again, when we run the limit as n goes to infinity, this Riemann sum transforms into what we call the definite integral. By analogy to what we did with derivatives, the Riemann sum is analogous to finding the slope of a secant line, or an average rate of change. That is the Riemann sum. When we take the limit of a Riemann sum, it's analogous to us taking the limit of a difference quotient, or the limit of the slopes of secant lines. So by taking the limit of this Riemann sum as n goes to infinity, we are approaching, in the sense of a limit, getting closer and closer to it and decreasing the error down towards 0 as we are approaching the exact value of what is called the definite integral. When we did that with derivatives, we took the limit of the slopes of secant lines, and that limit of the slope of secant lines was what gave us the derivative, which we interpreted as the slope of the tangent line, or the instantaneous rate of change. Okay, so I just want to be clear about that. When there is a finite number of areas, okay, that is the Riemann sum. Okay, when we take the limit of that, okay, when we take the limit of that as n goes to infinity, that's what creates the definite integral. Okay, so in this case, we have f is strictly positive, and so when we evaluate each of our f of xi stars, for instance, that's going to give us heights of rectangles, and then we can multiply that by delta x, where delta x is the width. And we're going to take delta x to be b minus a divided by n. That means we would be on a uniform partition then of the closed interval a to b. Okay. And there are multiple ways in which we can choose our xi stars. In this first example here, let's say we do the Riemann sum. Just take a look at Riemann sums right now. I'm going to use left endpoints for this first one. So what we did is we said, well, so we would subdivide this up into some finite number of subintervals, right? Let's say I take this, and then et cetera, okay, until eventually we take one out here, right? So we have subintervals here. Each has a width of delta x. Okay, now let's say I label a as the first x value. I'm going to call it x naught, though. If you recall, in order for us to create n subintervals, that actually requires we have n plus 1 values on the x-axis to mark. So if a is equal to x naught, okay, then this line right here would be where x1 is, and then this line can be where x2 is, and this line would be x3, etc., down the line. Okay? And ultimately, I'm going to call b x sub n. That way, since we started at x naught and ended at x sub n, we have a total of n plus 1 x values. This value right here, just before b, that would be x n minus 1. Okay, x sub n minus 1. Now, for any two of these x values, okay, the difference between them would be delta x. Right? So delta x can be expressed as the difference between any, let's say, x sub I, for any value I you could select from 1 to n, minus x sub I minus 1. Okay, so that would be true for I is equal to 1, 2, ... up to n. So, for instance, if you take I is equal to n, then this would tell us that delta x can be found by doing xn minus xn minus 1. That would be the difference between these two values right here, and that is a delta x. And if n is equal to, let's say, 3, then this would say we have delta x is x3 minus x2, which is true as well. That's the difference between these two x values here. Okay, all the way down to where n is equal to 1. When n is equal to 1, we're taking the difference between x1 and x naught, and that would be this difference right here. Now, we would not plug n is equal to 0 into this formula because that would require us to go to some x negative 1 value, which doesn't exist here, right? That goes outside of our closed interval. Okay, so this reasonably defines delta x, okay, for this choice of subintervals. Now, if we're going to be using left endpoints, that means that we're going to be evaluating the function f to find the height of the rectangle by using the left edge of each subinterval. Okay, so here's what that would look like. Our first rectangle would have, at this corner right here, the upper left corner of this first subinterval, that's where we're going to determine the constant height of that rectangle right there. The next rectangle over the next subinterval from x1 to x2 is going to be found, sorry, the height of that rectangle is going to be found at f of x1, for instance. All right? And then f of x2 is going to be the height of the next rectangle. Okay, over here on the other side, the last rectangle we choose here, its height is going to be determined by f of xn minus 1. All right, so that's f of xn minus 1. That's going to be the height of our last rectangle. Over here we had the first rectangle was at f of x naught. Okay, the second rectangle's height, that is at f of x1. The third rectangle's height was at f of x2. So the xi stars, when we're doing left endpoints, the xi stars would start at x naught, and then x1, and then x2. Okay, and the last xi star when choosing left endpoints would be x sub n minus 1. Okay, so in general then, that means that xi star, see if we can come up with a formula for that, right? Here's some examples, okay? So the first x star value, that would be x1 star, represents the x value we're going to be choosing in the first subinterval. We said right here by left endpoint, x1 star would be x naught. Okay, x2 star, that's going to be x1, right, etc. Okay, and the nth x star value, xn star, is going to be xn minus 1. That's by the left endpoint rule. So in general, xi star can be thought of as being xi minus 1. Right? So for instance, x2 star is equal to x2 minus 1. That's x1. Now let's try to put this in terms of delta x, okay, and let's say I and a, because when we are going to be looking at the notation for a definite integral, we're going to have constants for a and b, and we can use the constant a so that we don't have to go inside the interval every time we're evaluating an integral. We don't want to have to go inside of the interval and find all the individual x values we may need for evaluating it. And so getting set up for that right now. Okay, so in general, the xi minus 1, okay, is equal to a. For instance, if I is equal to 1, then we want this output to just be x naught, which was a by this left endpoint rule. Okay? But it's not always going to be a, otherwise we'd always be stuck by choosing a as the input for every subinterval. We want the next one to add a quantity of delta x to that, right? So when we choose the second, all right, when we choose x2 star, we hope to get a plus the width of one rectangle. So we're going to add, okay, the width of one rectangle. The width of a rectangle is delta x. Okay? If, for instance, if the input if I is equal to 2, we would want to be adding only one such width. So I minus 1 delta x. This is our formula for xi star. Let's check this and verify this. Xi star if we're using a left endpoint rule. So, for example, if we wanted to find out where is going to be x3 star, that would be what is the input we're going to use to then determine the height of the rectangle on the third subinterval. That would be 1, 2, 3. This subinterval right here, by the left endpoint rule, we expect x3 star to give us the value of x2. Okay? The value of x2 when we are evaluating x3 star. So if we plug I is equal to 3 into this formula, what do we get? Well, 3 plugs in for I. 3 minus 1 is 2, so we're going to add 2 delta x's to A. 2 delta x's added to A. A is this fixed value right here, and if we add the width of 2 rectangles, that would put us right here, and that puts us right at x2. Okay, so again, by rewriting the formula this way, notice what this gives us a reliance on having to know which quantities. Instead of us having to know the previous x value, of which there could be hundreds of them, thousands, millions of them. Instead, this tells us that for any individual xi star that we may want to find, we need to know what is the left edge of the entire closed interval, what is the width of each interval, that is on a uniform partition, and which interval is it that we're asking to look in? That would be I. So if I wanted to know what is the, what is x sub 100, if we had more than 100, say there was a total of 1,000 of these, but I want to know where the 100th one was. Well, that's going to be equal to A, which we already know what A has to be, and we're going to add 99 times delta x, where delta x is also dependent on B and A and N as well. So we wouldn't actually have to know all the individual x values. What we would want to know would be how many rectangles and subintervals are we trying to create? That's n. Where is the left edge and where is the right edge of the closed interval overall that we're integrating over? Okay? And which subinterval is it that we're asking to look in at the moment? That's what we would need. Okay, so that would give us by the left endpoint rule. And so if we were to write the Riemann sum by using the left endpoint rule, then it would look like this. I equals 1 to n f of this quantity. A plus the quantity a minus 1 delta x. All of that is the input to the function f, and then that gets multiplied by delta x, where delta x is, again, b minus a over n. So formulaically, how would we be able to write using, let's say, right endpoints now? Okay, let's try this out. Use right endpoints. The Riemann sum. Okay, so again, we're going to break up this closed interval, okay, into a bunch of subintervals, etc., etc. Okay, so again, I'm going to start by calling this x naught. I'll call the next one x1, the next one x2, the next one x3. B is again going to be called x sub n, and the one just prior to B would be xn minus 1. Now let's say we're using right endpoints over each subinterval. That means the height of the first rectangle would be found from x1. Alright? Right there. So f of x1 is going to be the height of the first rectangle. And then we're going to multiply that by delta x, the same delta x that we used from before, because again, we're creating a uniform partition. The next, okay, the height of the next rectangle would be found using x2. So if x2 puts us on the function right here, then the second rectangle has that height right there. That's using the right endpoint. So that's at f of x2. x3 would then give us, through the function, the height of the third rectangle, f of x3. The last rectangle we choose is going to have a height determined by x sub n. This one happens to be at 0 there, and that's not always going to be the case. But for this particular function, that's what we have. What is going to be the case all the time is that when we use right endpoints, okay, we're going to be choosing as our last, okay, as the last endpoint that we choose by right endpoints, we're going to choose x sub n. And so we'll evaluate f of x sub n in order to find the height of the last rectangle there. So our Riemann sum is again going to be written standard form of a Riemann sum. I equals 1 to n. That's sum f of xi star delta x. Let's write this in terms of our right endpoints now. So we'll see, for example, that when we choose the very first x star, that is x1 star, by right endpoints, that would just give us, well, x1. And choosing the second one, x2 star, that's going to give us x2. The third, x3 star, that's going to give us x3. Well, that seems pretty easy as long as we know every single one of these x values already. But of course, if there were like a million of these or even a billion of these, since we're going to be pushing n to infinity, we can imagine there's going to be an uncountable number of these. Rather than us having to actually go through the work of finding out every single x value that there is down here, let's instead try to put this in terms of the quantities that we will know from the start. That is, when we're given the notation for the definite integral, we're going to know what a is, we're going to know what b is. And when writing a Riemann sum, we're going to choose ahead of time how big n is going to be. Okay, so we already know b, we already know a, and we know n. That's, of course, how we get delta x as well. So xi star, what is a formula that we can come up with for that? It looks like xi star, from this, it looks like xi star is just equal to xi. How do we put that in terms of quantities like a? Well, let's say even on the first one, the first one, x1 star, which is equal to x1. Well, that's not equal to a, but that would be equal to a plus a single instance of delta x, right? The width of one rectangle. Well, by the time we choose the second x star value, that is x2 star, we expect to be right here at x2. That can be found by adding to a the width of two rectangles. So if the subscript I, that is telling us how many delta x's we would want to add, okay, to the left edge of our closed interval a. And this gives us the right endpoints. All right? This gives us the right endpoints for each one of our subintervals, which we can then use to evaluate the height of the associated rectangle. Our Riemann sum then, in terms of right endpoints, would look like sum I equals 1 to n of f of this quantity right here. That would be a plus I delta x, right? So now we're inputting the xi star values into the function f. That gives us our heights, but then we multiply by the widths delta x, okay, in order to get our areas. Okay, so similar, right? These both started out the same. They're Riemann sums. By using left end points, the input value was this, a plus quantity I minus 1 times delta x. But the input with right endpoints was a plus I delta x. Okay? And then in each case, we multiplied then by the uniform partition width, which is delta x. Okay. Now we also did the midpoint. So let's take a look at how this would, right? How would the midpoints be found? How would that look like in a Riemann sum, that is? So if we still start with a is equal to x naught, and we'll say that b is equal to xn, again, so there's going to be n plus 1 of these x values then in total. Subdivide this, 1, 2, 3, so on and so forth, and one more at the right edge for good measure, right? So here we have our x1, our x2, our x3, and finally this is our xn minus 1, right? Xn minus 1, like we had from above. Okay. But now we're going to be choosing midpoints. Okay, the midpoints of each subinterval. So for instance, on the first subinterval here, the height of the rectangle is going to be found if we go halfway between a and x1. Halfway between those two, we choose a new x value, which I'll do in green here, and that value then gives us the input for the function that then tells us the height of the associated rectangle. And remember that that is going to then balance out a little, in general, is going to give us a little bit of an overestimate and a little bit of an underestimate over that subinterval, which are going to kind of cancel each other out. Okay. And within the next subinterval between x1 and x2, we'll take what is halfway between x1 and x2 and then use that as the input value into the function to ultimately find out what is the height of the rectangle over our second subinterval. And so on and so forth. The third subinterval halfway between x2 and x3, we find a new x value. That would be our third x star, so that would be our x3 star. And we use that then to evaluate the height of this rectangle here. Alright, so we have like an f of x1 star, right here, the height of this rectangle. We have an f of x2 star, the height of this rectangle here, and an f of x3 star for the height of this rectangle here. And over here at this last interval, all the way over at the right edge, halfway between xn minus 1 and b, we find another x value, and then we evaluate the function at that x value. There's using our midpoint right there. Okay, so that would be on our nth subinterval. So this, the height of this rectangle would be f of xn star. Now our Riemann sum in general, regardless of which star approach we choose, is the sum from I equals 1 to n of f of xi star times delta x. We're still choosing delta x on a uniform partition. That's b minus a over n. All right, now with the midpoint, what's a formula we could come up with for our xi star? I'm going to use some notation here that is from from statistics with the bar over the top. So that means that we are taking the arithmetic mean or the average, an arithmetic average. So it's where we add quantities together and divide by the number of quantities we added together. So here we'd be taking the average of two quantities. Okay. So for instance, we're going to have our first star value, our x1 star, was calculated how? That was calculated this value right here, and that is the average of these two quantities, a and x1, where a is equal to x naught. So we can say it is x naught plus, we take x naught plus x1 and then divide by 2, or 1/2 times the sum of those two. Our x2 star would be found by adding x1 and x2 and then dividing by 2. So 1/2 x1 plus x2, etc. So in general, if we wanted to calculate an xi star, well, we're going to take a 1/2 of a sum, and the sum of what? Take this as an example. x2 star, the sum that we looked at was x1 plus x2. So for an xi star, we expect to take 1/2 times x sub 1 less than I, so xi minus 1, plus, and then for x2, that would be just xi. Now we can put this in terms of a and delta x's as well. Okay, so for that I'll go down here. So our xi star, which is xi bar, then, okay, how else can we write that? Well, the first one we might notice that we'd say is a plus 1/2 of a delta x, right? But the next one over, like x2 star, would be a plus 1.5 delta x's. Okay, so in general, our xi stars, looks like would be, well, if let's say I is equal to 2. If I is equal to 2, then we would be adding 1.5 delta x's. So I would say I minus 1/2 times delta x then. There we go. That's using midpoint. So for example, if we wanted to find out what is x3 star, right? x3 star by this formula would be found by taking a plus 3 minus 1/2, which is 2.5, delta x's. That is, we can add 2.5 rectangular widths to the left edge A to find the third, right, the third midpoint. That would be this value right here, can be found by taking A, the very left edge, and adding 1, 2.5, right, rectangular widths on a uniform partition. Okay, so these formulas take some time to develop, and hopefully we understand them geometrically. Now, in order to get what we're going to call the definite integral, which is hopefully the exact area under the curve, we're going to need to take the limit of our Riemann sums, again, as n goes to infinity. That is, geometrically, as we increase the number of subintervals, and hence increase the number of rectangles. As we increase that number of rectangles, as we have already demonstrated in a previous section, hopefully we've already been able to see that this is so. When you have a nice function here that is integrable, if you increase the number of rectangles that you use for approximations, you're going to decrease the error and get closer and closer to the exact value, and that's exactly what we're going to do. Now, notice that regardless of whether we choose left endpoint or right endpoint or midpoint or any other point that we could have selected, if you take any subinterval that you want to choose, whether you choose left, right, or mid, if the next part of the process is to increase the number of subintervals, that means each individual subinterval itself will have to shrink. So imagine then if we were to like double the number of subintervals, then each of our subintervals here would have to be cut in half on a uniform partition. So if we had left, right, or mid, but then if we came along and increased n by doubling it, all right, then the new subinterval would be half the size, and then our left, right, and mid, okay, our left, right, and mid would generally change where they are, but notice that they are now closer together. And then if we had then again, let's say we doubled the number of subintervals again, that is to cut each rectangle in half again, the left, right, and mid values again are getting closer and closer to each other. And we can see here iteratively, if we just keep doubling, for example, the number of rectangles, hence each time we double the number of rectangles, we are cutting the size of the subinterval in half. Every time we do that, we are pushing the left, the right, and the midpoint of each subinterval closer and closer together, till eventually we would have enough subintervals selected, right, such a large number of them that the associated subintervals would be sufficiently small enough that once those subintervals are really small enough, the left endpoint, right endpoint, and midpoint are essentially indistinguishable from each other. And the distance between them becomes negligible. If we can imagine that occurring, what's going to happen then as the limit as n goes to infinity, as a result of that, the limit by the left endpoint rule, and the limit by the right endpoint rule, and the limit by the midpoint rule are all going to approach each other as a single value. Okay? Now, the left endpoint, right endpoint, and midpoint Riemann sums are not going to be the same as each other, but the limits as n goes to infinity of all of those Riemann sums will be equal to each other. I hope we can see that that's what's going to happen then geometrically. All right, so if we take I equals 1 to n of f of xi star delta x, okay, by left endpoints, okay, let's call that L sub n. There is a finite number of these rectangles here. Okay, let's say the sum I equals 1 to n of xi star delta x by the right endpoints is equal to r sub n, and the sum I equals 1 to n of f of xi star delta x by the midpoints, we'll call that m sub n. L sub n is not the same as, but maybe approximately equal to r sub n, which is also not the same as, but approximately equal to m sub n. Right? These are not equal to each other. Okay? But by continuity of f, as long as f is sufficiently continuous on the closed interval a to b, then the limit as n goes to infinity of L sub n. That's if we were to do the left endpoint rule with an uncountable number of subintervals, okay, versus the limit as n goes to infinity of R sub n versus the limit as n goes to infinity of M sub n. All of these limits are exactly going to equal each other by the geometric reasoning I've just described. As we push n to infinity, it's going to increase the number of subintervals, but since the closed interval from A to B is not increasing as well, then what happens is each subinterval then shrinks. As n gets larger, each subinterval therefore gets smaller. And as the subintervals get smaller, eventually they would get small enough so that the left endpoint, right endpoint, and midpoint are going to be so close to each other, the same as when we had defining the derivative, that we had the slope of the tangent line can be geometrically interpreted as there is a point that is in motion along the curve and it is getting closer and closer to another fixed point. Eventually those 2 points are close enough to each other, though they never actually equal each other, but they become close enough to each other for us to define exactly where that limit is going. The same thing is happening here. And when that happens, then regardless of which formula we chose by the Riemann sum, I equals 1 to n of f of xi star times delta x. When we take the limit of this Riemann sum as n goes to infinity, these are all going to approach the exact same value. And that value, we say, if it exists, is the definite integral. That's what we mean when we say we have a definite integral. As long as the function f is greater than 0, we interpret this answer as the area under the curve that is bounded above by the function f, bounded below by the x-axis, and bounded to the left by the line x equals a, and to the right by the line x equals b. Right? If f happens to be positive, right, then we're talking about here the area of this region that is bounded to the left at x equals a, bounded to the right by x equals b, bounded above by y equals f of x, and bounded below by the x-axis, and the x-axis has, of course, the equation y is equal to 0. So it have 4 bounds around it. If f is greater than 0, we interpret this definite integral as that area. The notation to relate these to each other that we have, this symbol is the integral symbol. It is an elongated s. It is interpreted as the limit, okay, the limit of a sum. And what sum we're talking about is the Riemann sum. Okay? So the Riemann sum again is this finite sum right here. Okay? The Riemann sum is that finite sum right there, where it is it is the sum of a finite number of rectangular areas, is what the Riemann sum is. When we take the limit as n goes to infinity of that Riemann sum, if that limit exists, the value of that limit is the definite integral. So this elongated s is the integral symbol. It is the s stands for summation, but it is not just a finite sum. It is the limit of a sum. Okay, this limit right here. It is this notation right here. Okay, that is being represented by that integral symbol. Okay, so then when we write the integrals going from a to b, okay, the a and the b are the upper and the lower bounds of a closed interval. Right? So those are the bounds. So we're going to call this up here the b, that is the upper bound, and a down here, that is the lower bound. So we would expect in general for b to be greater than a. Certainly if we write it in this order, it implies that b is greater than a. Okay? If we were to see an integral that were written whereby the value of b was on the bottom and value of a was on the bottom for some reason, like if we had an integral that was maybe from 3 to 1 instead of 1 to 3, well, that would still be interpreted as over the interval from 1 to 3, but it would actually be read in reverse. It would be read in that direction. But as an introduction here, we're going to say we expect the value down here to be the lower of the two values and this one to be the upper of those two values. If they were switched, if you had the higher value was on the bottom and the lower one was on the top, what you could do is you could switch them here. You could flip those two numbers with each other, and then you could put a negative sign in front of the integral, and that's how you could deal with that situation. So we have an upper bound, we have a lower bound. Okay. Now the integral symbol comes with the differential. We've studied differentials before in this class as a thing all by itself, like for error approximation, for example. Okay. And we've also first saw it within the notation of the derivative, and it kind of has the same interpretation here for both of those interpretations apply here, really. Okay, it is notation that tells us the variable of integration. Okay, the variable of integration, so the variable for which we are interested in. Okay, by analogy, that is like what we had when we had the Leibniz notation, when we had something like df dx versus something like df dt or dh dt or something like that. All right, or dv dt was another one, right? The dx and the dt, whatever is in the denominator, that differential tells us which is the variable of differentiation when we're using this notation. Well, in integrals, this this differential is telling us which variable is the variable of integration within our function. So if we ended up with a function that was something like 3x plus t squared, okay, and it was from like 1 to 2 or something like that, we look at this as, well, this is a multivariable function. If we were to integrate this, which is the variable here, right? Is it both of them? Is only one of them? This is indicating that there's only one of them. We would then want to look at the differential over here to determine whether x was the variable of interest or whether t was the variable of interest. The same as we would when we were dealing with differential operators. Okay, the notation in the denominator would tell us, okay, which was the variable of interest, okay, to differentiate with respect to. Okay, now when you put all these pieces together, you have the limit of a summation of a bunch of areas over a closed interval from a to b, okay, using the function f of x, which is going to be in general going to be nice and continuous for us, times dx. Taking all this together, we call this the definite integral. What is it that's definite about the integral? The definite integral is going to be equal to a number if it exists. That's what's definite about it. Recall that by analogy, when we did this with derivatives, okay, so I'm going to say analogous to when we did f prime of a. Recall that f prime of a was the slope of the tangent line, or the instantaneous rate of change of the function f at a particular point. It was at the point a f of a, right? So this geometrically, okay, we would have, if there was a function and if there was a specific point with coordinates a f of a, what f prime of a is telling us, okay, it tells us the slope of this particular line right here, this specific line. Therefore, when the limit of the difference quotient existed, right, as long as the limit existed, this would equal a number. Okay? In the same way, this integral right here is a definite integral. It is equal to a number. Okay? And that number can be interpreted as the net difference in areas. That's what we're going to see, is that, so in general, if we have a function that is somewhat above the x-axis but also goes below the x-axis, for instance, something like that, but then if we bound it maybe from some a to some b, okay, something like that, what we're saying this definite integral then represents geometrically is we would take this area here, we would take this region as an area itself, let's call this one a1 and call this one a2, the definite integral in this case, a to b, f of x dx, is equal to the difference between a1 and a2. I said to interpret this as an area. That means I'm interpreting this as positive. Okay, the reason we're subtracting is, well, consider that the actual output of f, what is f of x right here, for instance? F of x itself is a negative number. Okay, I don't want the area to be negative, so instead I'll determine the absolute value of f of x times dx, okay, but the value of the integral is going to give us will actually be a difference between these two geometric areas here. As long as we have a left bound and a right bound and a nice function that we can integrate, this is going to equal a number then, just a number, and that number can be interpreted as the difference in areas from above to below the x-axis, okay, over the closed interval. Okay. In a future section, we will see that there is also something called an indefinite integral. If we write the integral f of x dx where there are no bounds, okay, there's no upper bound, there's no lower bound, okay, that is called an indefinite integral. And that is analogous to when we previously defined the derivative as a function, when we defined f prime of x. Recall that f prime of x, okay, f prime of x was a function, okay, a function with its own domain that we could then graph f prime of x, and we could take a look at the behavior of the derivative as it changed over its entire domain. If we plugged in a particular value of x into this, we would get the slope of the tangent line for that value of x. All right, we would get f prime of a if we plugged a into this. In the same way, our indefinite integral is going to output a function. Okay, this is an indefinite integral. This is going to be a function. Okay, so this is going to output a function, and for that function, if we were to evaluate that function that we get from here, we would get a number. And then we can interpret what that number is, and we'll see what that is soon enough in a future section. Okay, so here's our notation for the definite integral and a relationship we have to the Riemann sum, including the left endpoint, right endpoint, and midpoint rules. So we now know what a Riemann sum is. We know the notation for a definite integral, and that the definite integral represents the limit of a Riemann sum as n goes to infinity. And by analogy, we related these ideas back to how we learned how to do derivatives as well. They both require the use of a limit of a quantity that is maybe computationally expensive in that it's a lot of work to find, but is geometrically relatively easy to understand. What I'm talking about is when we did this with the derivative, defining the derivative, we started with the geometric reasoning of what is the slope of a line. And the slope of the line is not that difficult to calculate by itself. What's difficult is when we have to do it again and again and again and construct the sequence and then take a look at the limit of the sequence, okay, in order to define the derivative. But the actual slope of a singular line between two well-defined points itself is not difficult. Here, the area of a rectangle is not really that difficult is not that difficult to calculate. If we know the length and the width of a rectangle, we just multiply the two, we get its area. What becomes challenging here is that we're going to be doing this to n rectangles, and we have to do this both generally and for specific functions as well. Okay, and then we had to add the nuance of whether we're choosing left endpoint, right endpoint, midpoint, for instance, and then apply the limit. Okay, so since these definite integrals are interpreted either straight up as an area, as long as f is greater than or equal to 0, we just interpret it as an area and that's it. Or if f possibly also goes negative, we would interpret it as a difference in the areas from above to below the x-axis. We can therefore evaluate our definite integrals simply by using geometric reasoning, like areas. But we can also evaluate our definite integrals when we are given one by writing the definite integral in the form of a Riemann sum and then evaluating the limit as n goes to infinity of the Riemann sum. Okay, those are the two ways we have now for evaluating integrals. The midpoint rule, when you're asked to do that, suggests that the Riemann sum specifically that you would be constructing would be the one with the midpoint, okay, with the midpoint in it. And furthermore, you're calculating, by the midpoint rule, you're doing a Riemann sum that's just a finite number of rectangles. Notice there is no limit here. Okay, this sum right here is going to be an approximation to the integral. If we wanted that approximation symbol to turn into a strict equality symbol, that would require us taking the limit as n goes to infinity of this sum. Okay, which again, recall, would not require the midpoint rule. It wouldn't matter which rule we chose if we were going to take the limit in the end anyway. So you'll see some exercises in the homework where you're asked to do the right endpoint rule, and sometimes we're asked to do the midpoint rule. Here's one right here. Evaluate the Riemann sum for a given function over a closed interval, so there's an a and a b, with 5 subintervals. So n is equal to 5. Okay, take the sample points to be right endpoints. So this is asking you to use the right endpoint rule in order to evaluate a Riemann sum for a particular function. Furthermore, to explain what you're doing geometrically with the aid of a diagram. And that is, we should be graphing f of x over the interval from -6 to 4. So pick which one is that, okay? Which one is that, and which one also represents where the individual rectangles would be, okay? If we're choosing right endpoints. So if we have this, if this is the graph of f of x equals x minus 1, right, it's a linear equation, slope of 1 and y-intercept of -1, if that's its graph, we want to see from -6 to +4, are we choosing the x star values on each of 5 subintervals? Are the x star values being chosen at the right ends of those subintervals? Well, so the subintervals from -6 to 4, b minus a, that would be 4 minus -6, that's equal to 10. So b minus a is equal to 10. Divide that by 5, you get 2. The width on a uniform partition here, the width of each subinterval is equal to 2. So here's the first subinterval right here. If this is the first subinterval from -6 to -4, then our first x star value by right endpoints should be at the right edge of that subinterval. That means that -4 we should be selecting as the input to our function to determine the quote-unquote height of the first rectangle. But if this is the height of the first rectangle that is over this subinterval, then this particular graph is not representing that. It looks like this image right here is representing where we're choosing the left end point of this subinterval to determine what is the height of the first rectangle. And I say quote-unquote height because this is a rectangle that exists below the x-axis. In other words, we can still determine the absolute value of this as a geometric area, or we're going to need to take each of these quantities, if we were to calculate the areas of each one of these rectangles, okay, each one that is below the x-axis, we're going to want to subtract that amount instead from the ones that are above the x-axis. So which one of these 4 graphs has the function f of x equals x minus 1 and is choosing the rectangles with respect to the x-axis, okay, and using right endpoints? And here's another one for you to do. This one says use left endpoints in order to evaluate the Riemann sum. The function here, 3 cosine x, so you're going to be evaluating the cosine at different quantities of x. It says you're going to choose n is equal to 6, so you're going to have to evaluate this 6 times over. Okay, 6 times. And you're going to have to find the left end points. Here is your interval from A to B. So you're going to subdivide that into 6 subintervals. Choose the left edge of each of those 6 intervals as your x star values. You're going to plug those into the cosine so that then you can sum up the product of f of x star times the delta x. Delta x is found how? B minus a divided by n. All the formulas are given to you here in the notes and a couple examples that I worked through as well. Expressing an integral as a limit of Riemann sums. So here's a definite integral. This definite integral is written whereby we have the lower bound is equal to 2. That's a. A is equal to 2. The upper bound is 4. So b is equal to 4. Okay. And then the function called the integrand is the square root of 7 plus x squared. So that's our f of x for this particular example. You are not being asked to evaluate the result of this. No one's asking you to figure out what this integral is equal to yet. Okay? In fact, this is not an integral that you would be able to do until your next semester of calculus. But what you can do is you can approximate this integral by the use of a Riemann sum, and you can start here by writing it as a Riemann sum. Okay? So express it as a limit of Riemann sums. Okay? In general, I'll make a note here, in general, you're going to want to use, for our different choices for sample inputs, use the right endpoints for your sample points in general. Okay? That is what we derived over here. Okay, this formula right here. Okay, I'll put this one down here in a different color, so try to highlight it. Okay. In general, this is going to be kind of considered to be the least amount of work when finding sample inputs if you have the choice. Okay. If you just take a look at this compared to the left endpoint, the left endpoint is a plus the quantity I minus 1 times delta x, but this is a plus I delta x. So it's like one fewer operation. You don't have to subtract 1 from I. So it's a little bit easier than that, but certainly easier than the midpoint one, because the midpoint one, then you'd have to subtract the fraction 1/2. And so, this is just the least expensive of the types of endpoints, okay, to use. So use that formula there in order to write your limit of Riemann sums. So you're going to need to have your f of xi star for this particular function f, and for your xi stars chosen, okay, on this closed interval by the formula a plus I delta x. Okay, so we need to calculate delta x. You see what a is equal to. It's equal to 2. Okay, plug that quantity into f of x. There's other examples here whereby you can evaluate. Here's one with the midpoint rule. You click on that, it should open up a screen whereby it tells you what the midpoint rule is. Okay, which we already talked about. So whereas these couple of exercises here are asking you just to write the Riemann sum and then leave it alone, don't evaluate the limit, in these questions right here, you're being asked to come up with an approximation for the integral through the use of the midpoint rule. So for this, it's asking you to use the midpoint rule where n is equal to 4. So you're actually going to find the areas of 4 rectangles, if you will. Okay, if some of them are positive and some of them are negative, right? You're going to find the net difference in the areas then. Okay. But you're going to have 4 products you're going to have to calculate, and then you're essentially going to sum those up, positives and negatives, if applicable, over this interval. You're going from 0 to 56, subdivide that into 4 subintervals, use the midpoint rule in order to evaluate this definite integral as to approximate the definite integral. So you're not asked to find the exact value of this integral. This is an integral that you will not be able to evaluate in this course. Here's another one you will not be able to evaluate in this course, but you can approximate it. Again, this is asking you to approximate it by the midpoint rule, so to get practice with that. Okay. In these questions here, you can use the actual definition of the definite integral. What is the definition of definite integral? That is the limit as n goes to infinity of the Riemann sum. The definite integral is defined as a limit. Remember that the derivative was also defined as a limit. Anytime we had a question asking us to find a derivative through its definition, it meant use a limit. Limit as h goes to 0, difference quotient, right? Well, the definition of a definite integral also requires a limit, and this is the limit you need to find. So you need to write the Riemann sum, so you're going to have to find out what is f of xi star, and you're going to have to find delta x as well from the given information to write the Riemann sum, and then you're going to run the limit. Let's take a look at a couple examples in the notes for doing exactly that. Delta x is calculated by b minus a over n, and the xi by the right endpoint rule. The right endpoint rule would be found by a plus I delta x. Okay, so let's take a look at some examples from the notes. Okay, I'll give you a summarization of the process from the previous section where we were finding areas, okay, under the curves. Okay, here is your definition of the integral along with some notes about it. Okay. I discussed these notes already. Here, dx, the differential, is the limit of delta x as n goes to infinity. If you take a look at this expression here, b minus a over n, where b and a are constant, if we take n to infinity, then actually this fraction would approach 0, right? It gets infinitesimally small. Okay? But geometrically, that's not going to help us. If we look at the integral here, if we take the limit as n goes to infinity, and delta x is involved in the Riemann sum, if delta x were actually allowed to shrink all the way to 0, then the value of the area would always be 0. Because remember, geometrically, we're interpreting delta x as the width of the rectangle. And if the width of the rectangle actually went to 0, then we wouldn't have any rectangles left. So similar to what we did with the derivatives, we would push the 2 points along the curve. We would have a fixed point and a moving point. We would push the moving point, the variable point, towards the fixed point but we were not allowing them to actually merge, because if we did, we'd get an indeterminate form. That difference between x2 and x1, that delta x, would approach 0. Okay? Well, we wouldn't actually want it to go to 0, because then we wouldn't actually be able to calculate it. It would be undefined. So instead, we're saying, as n goes to infinity, this is going to get to 0 if we actually allowed it to, but it doesn't, because as long as n is never actually equal to infinity, right? It's actually equal to a really, really large value, okay, that is, uncountably large, then this fraction here never really disappears. It gets very, very, very small, and that is what the differential dx is representing. In the integral notation itself, for a definite integral, that is, the f of x, the function f of x represents the heights of our rectangles at every single value of x we can choose by continuity of the function on the closed interval from a to b. That is sufficiently continuous. It is possible for it to have some jump discontinuities in it, okay, but and we won't look at that in this course. Okay, point is, the function f exists for every x value from a to b. It exists now as a as a finite value, and the dx is interpreted as the width of each rectangle. So when we look at f of x dx, we're thinking f of x is the height of a rectangle, dx is the width of the rectangle, and so the product of the two gives us an area. And we're summing up, through the use of the integral symbol, tells us we're summing up an infinite amount of these areas, and we're choosing the values of x to be every single value from a to b on a closed interval, which by the density of real numbers means we're choosing an uncountable number of x values. We're evaluating f of x at every single value on this closed interval, and each one of those outputs is then getting multiplied by a really, really small width of a rectangle. Now, in order to be able to evaluate these definite integrals through the use of a limit of a Riemann sum, we would need to be able to evaluate certain summations, and this table here shows the evaluations of certain summations. The derivations, demonstrations of these are shown in the back of the textbook in the appendices. We won't need to see those derivations here. I showed a couple of them in a previous lecture video from 5.1. Okay, but we need to have these nearby so that we can evaluate these type of expressions in our summations. So let's take a look at where they might show up. Here's your first definite integral for us to officially evaluate here. So we have the integral from -1 to 2 of the function 4 minus x squared dx. Okay, the notation of the dx is important here. That needs to be included. It's the appropriate notation, just as we would include limit notation with evaluating limits, and just as we would include prime notation or the Leibniz notation when we're evaluating a derivative. And the dx, the differential, comes after the function. The integral symbol comes before the function. So it's so the integral symbol and the dx, okay, sort of sandwich the integrand. They go to the left and the right of the function that is being integrated. Okay, by using the definition of the definite integral, that means we're using the limit of a Riemann sum. Okay, the limit of a Riemann sum. And the standard choice for our xi stars to make with our Riemann sum is the right endpoint choice. And this was the formula for the right endpoint choice for the xi stars, a plus I delta x. All right. So for instance, for the first x star value, x1, x sub 1, if I is equal to 1, would be found by taking a plus delta x. That would be the width of one rectangle to the right of the left edge a. So the left edge is at -1. So I'm showing it here geometrically at -1, and the right edge is at 2. And our function 4 minus x squared I have graphed here in black. And so this region I've shaded in red, we are finding the area of that region, the exact area of that region, by taking the limit of a Riemann sum. Now the Riemann sum itself we're going to set up so that we have n subintervals and hence n rectangles, and we're going to allow n to be any number. We're not going to choose n, so that later we can take the limit as n goes to infinity. Here's the construction of the Riemann sum. Delta x is calculated b minus a over n. Let's find that. From here, we have that b is equal to 2, a is -1, and n is just n. So b minus a over n is 2 minus -1 over n. That gives us 3 over n. This is the width of each rectangle. If there were 100 rectangles, each would be 3/100ths in width. If there were 1,000,000 rectangles, each would be 3/1,000,000ths in width. And if we push n to infinity, this 3 over n is going to shrink to 0, but before it gets to 0, right, it is approaching the differential. The xi's by the right endpoint formula, a plus I delta x. Well, a, taken directly from the integral, is -1. I is just I. That's to tell us which subinterval we happen to be looking in at any particular moment. So that is changing. I is changing. I is going to start at 1, and it's going to go all the way up to n in the summation. And then 3 over n, well, that's what we just found for delta x. Right? So we take our delta x and we plug it right into this formula along with a. So we have -1 plus I 3 over n, or -1 plus 3i over n. That's our xi stars, -1 plus 3i over n. We plug our xi stars into the function f. That's why I'm writing f of -1 plus 3i over n. That's our f of xi stars, times 3 over n. Again, geometrically, what we're finding here is that for each one, all right, for each one of these xi stars that we evaluated at, f of this quantity, f of -1 plus 3i over n, that's a height of a rectangle. And 3 over n is the width of the rectangle. And so we're taking the product of those two, which is an area. Now, since we have a particular function here, 4 minus x squared, we can plug our xi star formula into our function. So 4 minus x squared becomes 4 minus the quantity, -1 plus 3i over n squared. That's a 4 minus x squared. Okay, that's our function evaluated at our right endpoints. Okay, for any particular subinterval I, for any particular choice of how many rectangles we want in total, n. And then the 3 over n out here is our delta x. Here is our Riemann sum. If we were to choose a particular value of n, like n is equal to 4, for instance, if we chose n equal to 4, we could plug 4 in for our n's here, and then we can evaluate the sum. I equals 1, plug it in. I equals 2, plug it in. I equals 3, you plug it in. Then I equals 4, you plug it in. Add up those quantities that you get, and that would be an approximation then to the area under this curve by choosing 4 rectangles and the right endpoint rule. By the definition of the definite integral, if we take the limit of this entire summation as n goes to infinity, we would get the exact area of this bounded region. So the definite integral is equal to the limit as n goes to infinity of this Riemann sum. And now we need to evaluate this limit. How do we do that? Start through algebraic expansion. So I start here. I'm going to FOIL this expression here. These were the right endpoints, right? The xi stars, which were being squared in the function itself, in f of x, right? 4 minus x squared. So I FOIL that out. So I get 1, and then I get minus 6i over n, and then plus 9i squared over n squared. So that's been FOILed. Now we can combine the terms here. 4 minus 1 is 3. And multiply by distributing this 3 over n as well. 4 minus 1 is 3. 3 times 3 over n gives us 9 over n. Distributing the negative. And then multiplying by 3 over n, we're going to get a positive 18i over n squared. And a negative 27i squared over n cubed. So we have these. Now, we can distribute the summation to a sum of terms. That is, the sum of a plus b plus c is the sum of A plus the sum of B plus the sum of C. So we can do that, and so I'm distributing that as well as the limit, as we know we can distribute a limit as well. Okay, like a linear operator, we can distribute a limit through a sum and a difference as well. So I'm looking at these 3 limits that then need to be evaluated. How do we evaluate those? First, within the summation, I say this right here in highlights, within the summation itself, the thing that is changing is I. Within the summation, that is, if we just look at the expression, right, to the right of this summation, the sum 9 over n, the only thing in motion is I. But there is no I in this expression, it's a 9 over n. So we take 9 over n as a constant with respect to the summation, because there's no I in it. Therefore, 9 over n can be factored out of the summation. And although 9 is also constant with respect to the limit, the denominator n is not constant with respect to the limit. So we can take the 9 and put it all the way in front of the limit, but the 1 over n we can only put in front of the summation, right, but after the limit notation. Okay? Here I've actually put the 9 in the n after the limit. You could put the 9 in front of the limit, because 9 is constant with respect to the variable n. But you can't take n out of the limit. You have to run the limit on the n. And if you had any I within the summation, you could not factor out that instance of I. That's why in the second term here, the 18, that could have been factored all the way to the front of that second limit out to here. The I in the numerator has to stay within the summation because we need to evaluate the summation with that I. And the n squared in the denominator can get factored out of the summation, but it cannot get factored out of the limit. Okay? Whatever is in motion has to remain, right, has to remain within that expression, okay, where it is in motion. Whatever is not in motion is considered constant. On the third one, we have a 27 in the numerator. 27 is constant. We could factor that all the way to the front of the limit. We could have put that after the minus sign and said 27 times the limit. The 1 over n cubed can be factored out of the summation, but not factored out of the limit. Right? Because it has to follow after the limit because the limit has n in motion. And the I squared has to remain within the summation. Now, how do we evaluate the summations? That's where we go back to the table, right, from the previous page of summations that we need to be able to evaluate. The sum I equals 1 to n of 1 would be n. The sum I equals 1 to n of I would be n times n plus 1 over 2. And the sum as I equals 1 to n of I squared is n times n plus 1 times 2n plus 1 over 6. That's how we can evaluate those summations, those individual summations. Those three we're going to need for this example. Okay, the other ones, if we had the sum I equals 1 to n of a constant c, it's going to be n times c. That's the same as factoring the constant out of this summation here. And finally, if you run into an I cubed in one of your definite integrals, this is how you evaluate the sum of I cubed. And that's as much as you would need to know for this particular course. Okay, so there's our sums. Let's use what we have from this table to evaluate our sums, right? So we had a sum I equals 1 to n of 1, which from the table is just n. That is, in other words, what's 1 plus 1 plus 1 plus 1 plus 1 n times over. If you add 1 to itself n times, you get n. The next one, we have the sum of I from I equals 1 to n. That is n times n plus 1 over 2 for the summation, right? We haven't run the limit yet. We evaluate the summation. And the sum of the I squareds from above, n times n plus 1 times 2n plus 1 over 6. Now notice we have three expressions here, which are really actually rational expressions. All right, and each of them we can run the limit as n goes to infinity as the limit of a rational function. Okay, the same as we did previously in the course where x was going to infinity for such expressions. We're going to get, in general, infinity over infinity. All right, so like take a look at this one. We're going to have an 18 times n plus 1 is, if we were to expand this, we're going to have the leading term is 18n squared. And then we're also going to have plus 18n. So if the leading term is an 18n squared, okay, and then the denominator we also have a 2n squared, recall that with rational limits that are going to infinity over infinity in indeterminate form, okay, we can compare their degrees, and if they have the same degree, we can divide the leading coefficients. And that's what we have in this case. The leading term up on the numerator is 18n squared. The leading term of the denominator is 2n squared. The numerator and denominator each have a degree of 2, so we can divide their leading coefficients. The other approach we had from previously in this course is to divide all of the terms by the highest power term in the denominator. That is the term that got to infinity first, or the term that was growing the fastest. Okay, so we want to take a look at that. That approach again, just as a reminder of another way you could evaluate this limit. The limit as n goes to infinity of 18n squared plus 18n over 2n squared, right? One way is to compare the degrees. If the degree is the same, okay, then you just divide the leading coefficients, and that's how you evaluate the limit, right? We learned that in pre-calculus class. Okay, but also here in calculus, okay, we learned that we can divide each term by the highest power term in the denominator. That is the term that is getting to infinity the fastest, or growing the fastest. So I'm going to multiply the bottom by 1 over n squared, and I'm going to multiply the top also by 1 over n squared. So we get the limit as n goes to infinity of what? 18n squared over n squared plus 18n over n squared, and the denominator we have 2n squared over n squared, and now we can run each of these limits here. All right, so 18n squared over n squared is going to 18. 18n over n squared is going to 0, and 2n squared over n squared is going to 2. So when we run all these limits, we are left with 18 plus 0 over 2, but that just equals 9. Okay, so this is the calculus approach to this. In pre-calculus, although you learned the method of comparing the degrees, you didn't learn it necessarily within the context of a limit, most likely, but instead with respect to end behavior and asymptotic behavior. Okay, so a more algebraic approach. The other approach of dividing by the function that grows the fastest is a more calculus approach to the same question. And in one other way, when we have an indeterminate form, infinity over infinity, we could, of course, apply L'Hopital's rule. All right, that was another way that we could have done that. So you could say the limit as n goes to infinity. Let's say I write it as the limit as x goes to infinity. 18n squared plus 18n over, 18x squared plus 18x over 2x squared. Okay, I'd like to write it this way because this makes it continuous, because if we want it to be continuous, because we're about to apply L'Hopital's rule, and L'Hopital's rule requires that we take a derivative. And you can't take a derivative if it's not continuous. Why is this not continuous? Because n is a natural number here. So we're going from n equals 1 to 2 to 3 to 4 without touching all the other values in between. And by changing this to x, I just made it continuous. So if I did L'Hopital's rule here, right, because we have an infinity over infinity indeterminate form, right, and we take the derivatives, right, 36x plus 18, and then the bottom is going to be 4x, right, and that's still equal to, that's still equal to infinity over infinity, so I'm going to do L'Hopital's rule again. So the limit as x goes to infinity, this is going to be 36 over 4, and now this is just the limit of a constant, and that just equals the constant, so we get 9. All right, so there's a variety of approaches you can use to evaluate these types of limits that you're going to get. Okay, so looking for a proper notation here, you're going to have to do you're going to have to set up whatever delta x is. You're going to have to set up your xi stars. I could put a star in there. That's what's intended. These are your xi's, or your xi stars. You're going to have to plug that into the individual function, whatever particular function it happens to be. Simplify algebraically. In this particular case, that required a FOIL and then distributing, for example. But that was just because of the nature of the particular function that was given here. I mean, if the function was something like the sine of x, you're not going to have to be doing all that distributing and stuff. You're going to have the sine of, -1 plus 3i over n, and that's going to be times 3 over n, for instance. And by the way, that type of integral, we're going to have to talk about how to do that, okay, in a future section, something like a trigonometric integral. Okay, we'll take a look at that soon enough. But for these right here, wherever you'd have to be evaluating it by doing the limit of a Riemann sum, you're going to need to be able to write those Riemann sums in terms of expressions in this table. So I would only give you ones that are polynomial, if you're going to be using the table. So here's another one. Evaluate the integral from 3 to 5 of the quantity 12 minus 4x. Oh, and by the way, what did you get here? So you value, the sum. This sum was equal to 9, right? This one was equal to 9, and this one was equal to -9. Check the limit and see that you can get that this one is also equal to 9 right here, which we're subtracting. So 9 plus 9 minus 9 gives you 9. Therefore, this integral is 9. Now, geometrically interpreted, what we found is, because this function was positive over the entire interval, non-negative, that is from -1 to 2, the actual area of this region is exactly equal to 9. Okay, and that's a pretty solid conclusion to come to, because this region is not the shape of a rectangle. It's not the shape of a trapezoid, and it's not a circle or a semicircle, right? It's got a parabolic dome on it, and we're able to find its exact area. Okay, it's equal to 9. All right, evaluate by using the definition of the definite integral. So we got the integral from 3 to 5, 12 minus 4x dx. Okay, I made a note here. If you graph this, and we'll take a look at the graph in a moment, that it is in fact negative on this interval. Since the function, right, for instance, if we plug in 4, okay, right, I didn't include 3 here, right, in the closed interval, because at 3, this is actually equal to 0, right, but it is negative within this interval. So if you plug in like x is equal to 4, you get 12 minus 16, which is negative 4. So the output of this function is going to be negative when we are on this interval here. So we would have to be careful not to interpret the answer specifically as an area. Like, notice the answer is that we get is negative 8. Okay, go through the math using the table above, doing the algebra and everything, okay, to see that you get the same result. We actually get a negative 8 and negative 8. So our interpretation of this is not that the area is negative 8, but instead the area of the region itself would be positive 8. The value of the definite integral is negative 8. Okay, it's because the function existed below the x-axis. Our interpretation of that answer being negative, okay, comes within context of whatever the function itself was actually representing, if it represented something within within an actual application exercise. Okay, so let's take a look at the integral from 3 to 5, 12 minus 4x dx. Take a closer look at this geometrically. So the function f of x equals 12 minus 4x is linear. It has a y-intercept at 12, okay, and it has a slope of negative 4. Okay, so for instance, if x is equal to 3, this is going to equal 0. Okay, so we have 1, 2, 3, 4, 5, let's say. So here's 3. Okay, so the function is crossing there, right? This continues out in that direction in general, right? This is f of x equals 12 minus 4x. X equals 3, and then at x equals 5. 12 minus 4 times 5, 12 minus 20. That's equal to negative 8. All right, so the function goes off in that direction. When we're talking about this integral right here, we are saying that we are trying to determine what this is right here. Okay, so I'm going to give this one a name. Okay, I'm going to just call this one A. I'm going to call this A right here, where A is actually, I'll say A is the area of the shaded region. The area of the shaded region. Now, since area has to be greater or equal to 0, then that means in terms of our integral, A would actually be the absolute value of the integral from 3 to 5 of 12 minus 4x dx, right? That way it would be greater than 0, and so we can actually call it an area then. The integral itself is going to have the magnitude of the integral is going to be the area, but the integral being negative, okay, is going to tell us that the net area existed below the x-axis itself. Now, if we want to interpret it then as an area, A, we can do so by the fact that we know this shape. This is the shape of a triangle. All right? So let's use the area of a triangle instead of a Riemann sum. We already did it by the Riemann sum. We know what the answer is going to be, negative 8, right? Well, let's find A as an area of a triangle, and then because we can see its position below the x-axis, we'll say then that the definite integral is the opposite or the negative of that area. The area of a triangle is 1/2 base times height. Okay. Using our picture here, what's the base and what's the height? Okay, let's see if this right here is the base looks like it's 2, and if this is the height of our triangle here, right? This is 0, this is negative 8, looks like the height is 8. So the area of our triangle is 1/2 times 2 times 8. Multiply that out, we get 8. The area of that triangle is 8. Therefore, the integral from 3 to 5, 12 minus 4x dx, is negative 8. Right? The negative because it is below the x-axis entirely, and the 8 because that is the actual area of that region. Now let's say we wanted to interpret, how about from 0 to 5? Okay. The 12 minus 4x, the integral from 0 to 5 of 12 minus 4x dx. Okay, so that is where we're still using that graph above, but I'm going to quickly sketch it here again. Alright, so this is 12 right here. Alright, there's our f of x. Okay, it crossed at 3, and then we have this going to up to 5. Alright, I'll straighten that out. Alright, so that's to 5 right there, which we had that the y value there was negative 8. Alright, so we have this region down here, and we have this region up here. Okay, so now let's say I call this area up here A1. Okay, this is A1 right here, but then this one I'm going to call it A2. Okay, so we have A1 and we have A2. Okay, now from the picture, notice that one way that we're going to interpret this, okay, is as the net area. Okay, the net area bounded by the function y equals f of x, the x-axis, that's y equals 0, okay, the line x equals 0, the vertical line x equals 0, and the vertical line x equals 5. Okay, those are the bounds. So we have x equals 0. I should maybe sketch those in here, these bounds. This is a bound of the region, right? This is a bound for the region, right? This is a bound for that region, and this is a bound for the region. So anything that is enclosed within these 4 bounds, okay, is part of our definite integral. And that can be calculated now by taking A1, where A1 is the area of this region, and subtracting A2, where A2 is the area of this region. Okay? Where A1, okay, A1 is the integral. Can we write that area as an integral? A1 is the integral from 0 to 3 of the function 12 minus 4x dx. And A2, right, we're interpreting A2 now as an area. A2 is not just equal to this integral, but is equal to the absolute value of this integral, because this integral itself is going to be negative. How do you write this as an integral? It is the integral from 3 to 5 of 12 minus 4x dx. Okay? We already know that A2 is equal to 1/2 times 2 times 8, which is equal to 8. Okay? Right, we know the area down there is equal to 8. We calculated that before. What is A1 equal to? Similarly, not by Riemann sums now, but let's use geometric reasoning. Let's use the fact that this is a triangle as well. 1/2 base times height. Okay? Where now we have, let's see, the base of this triangle is 3, and the height of this triangle is 12. So let's calculate A1. 1/2 times 3 times 12. Okay, so 1/2 times 12 is 6. 6 times 3 is 18. So therefore, we have that A1 minus A2 is equal to 18 minus 8, which is equal to 10. And that would be then the integral from 0 to 5 of 12 minus 4x dx. Interpret it with areas. Okay, so we had a net difference in areas. We had a portion that was that was an area above the x-axis and a portion that was an area below the x-axis. We could determine each of the individual areas, which would be non-negative values then, and then we could subtract the area that was below the x-axis from the area that was above the x-axis. That's our interpretation then in terms of areas for this complete integral right here. Okay, here, definition of the definite integral. You can take a look through that example. On each one of these, I also ask that you please verify the limit values by using techniques and notations from this semester. So check to see that you get from this limit the same thing that I'm getting here, and that you can use the appropriate notation as well from previously in the course. Here's one in terms of areas. Evaluate this integral in terms of areas. Now, rather than trying to graph the function 1 plus the square root of 4 minus x squared, instead we can break it apart into different pieces. So we have the integral on the 1 and the integral on the square root of 4 minus x squared dx. The reason we can split it apart is the same reason that we can distribute a limit. The summation is interpreted as the limit, or the integral symbol is interpreted as the limit of a summation. And the summation and the limit are each things that can be distributed through a sum or a difference. I'll add it cannot be distributed through a product. So if we had an integral of a product of functions, we would need a special rule to be able to deal with the integral of a product. We would not be able to integrate each component of the product and multiply together. That would not work. That's easily enough seen when we take a look at, for instance, like the product of two sums with each other. Okay, the product of sums you would actually need to expand in order to go term by term. Anyway, you'll take a look at an integral of a product in your next semester of calculus. Here we have an integral of a sum. We can break it apart. Let's take a look at each integral then geometrically. The first one, we have the integral of the constant 1. So the function f of x is equal to 1. That's just the constant horizontal line y equals 1. And if it's bounded from -2 to 2, this is our region, right? It's bounded between f of x equals 1, the x-axis, x equals -2, and x equals 2. And that gives us a rectangle. We can easily calculate the area of this rectangle by its base, which is 4, and its height, which is 1. So 4 times 1 is 4. So this integral is just equal to 4. What about the other one? How do we interpret this geometrically? Well, get used to seeing these types of expressions. Okay, these can be interpreted both in terms of circles and circular areas, but also trigonometrically. Notice it's got a relationship here to the Pythagorean identities from trigonometry. But okay, so here's what we can say. If we created a function y equals the square root of 4 minus x squared, notice that first off, y would have to be greater than or equal to 0, because the square root is a principal square root, right? The right-hand side is not negative, therefore the left-hand side cannot be negative. That's the first thing to make note of, that y must be greater or equal to 0, because the principal square root is being used here. Now, if we square both sides and move x squared to the other side, we get the equation transformed into this, x squared plus y squared equals 4. And we know that is the standard form equation of a circle with a center at 0, 0, and a radius of 2. All right, because a circle's equation, standard form, is quantity x minus h squared plus quantity y minus k squared is equal to r squared. So h and k are 0 and 0, and the radius is 2. So we can graph the circle, but we only graph the upper half of that circle. Why? Well, first off, this had to be a function. A full circle wouldn't pass the vertical line test, but also, again, y is not negative because this is not negative. So we want the circle, but only where y is not negative. Hence, we have the upper half of a circle of radius 2 centered at 0, 0. And we want to know what is the area of that region, because the area of that region is going to be the value of this integral. It's entirely above or on the x-axis, so it is strictly interpreted as an area. And this is a circle, a semicircle, right? A half of a circle. So we can find the area of a half of a circle using the formula for the area of a circle. So a circle's area is pi r squared, r is equal to 2, and we take half of that. So half of pi r squared, where r is equal to 2, gives us 2 pi. Therefore, this definite integral is equal to 2 pi. Okay. You would not want to evaluate this integral by a Riemann sum. Okay, we're not going to do that in this course. And you're going to need a special kind of a substitution to do this integral by any other method, which you can deal with in a Calculus 2 course. For this course, this type of an integral needs to be interpreted correctly as an area, okay, or a difference of areas, if, depending on how the graph actually looks over the closed interval, okay, and that's how you're going to be able to evaluate that type of a piece, right? And again, when we evaluated this whole integral, we needed to also break it apart into two separate pieces and evaluate each piece, okay, separate from the other. We could have done that with this example right here. I'm going to take another look at this example, but let's say we broke this apart into a 12 and a 4x, okay? Or we could have done it with the original one as well. Go back to the original one. So we could do, let's see, from 3 to 5 of 12 minus 4x dx. Okay, let's take it as as two integrals. So from 3 to 5 of 12 dx minus the integral from 3 to 5 of 4x dx. Let's interpret each of these geometrically. So this one right here, we have y is equal to 12, okay, which is a horizontal line. So let's just say that's where y is equal to 12. This is the y-axis. Here's our x-axis. And then from x equals 3 to x equals 5, then we have bounds. X equals 3 and x equals 5. This region right here, okay, is what's being represented by this integral right here. Okay, so that region, we'll call that A, or A1. Okay, we'll just call that one A1. So the integral from 3 to 5 of 12 dx, which we've called A1, is the area of a rectangle, and this rectangle has a base of 2 and a height of 12, and that equals 24. Right, so this area is 24. Okay, so here's the base. Let's get blue here. All right, so there's the base right there. There's the height right there. Okay, base times height. So that's 24. What about this, right, this integral over here then, right? We've got y equals 4x. Y equals 4x is a line. It crosses through 0, 0, and it has a slope of 4. Okay, so let's take that. Y equals 4 times x. Here's the y-axis. Here's the x-axis. 1, 2, 3, 4, 5. Here's 3. Here's 5. Okay, we're bounding it on the left by x equals 3. We're bounding this region on the right by x equals 5. Okay, so this is the region right here, okay, that we're interpreting as this definite integral. I'm going to call that A2. Okay, there's a couple different ways in which we can calculate what A2 is equal to. Okay, the integral from 3 to 5 of 4x dx is equal to A2. Okay, that can be calculated as either a difference in triangle areas. We have a larger triangle and a smaller triangle, okay, or as a trapezoidal area. Okay, either one of those. Okay, let's say we use triangles. Triangles. So I'm talking about where we have a larger triangle here. I'll call this one B1. Okay, with this height right here, call this H1. Okay, so that big triangle, take its area and subtract from that. Let's say we subtract from that the area of this triangle right here, where we have B1, okay, and we have H1 right here. Oh, sorry, I mean B2 and H2 is what I should be saying. Okay, so let's interpret it that way. So we have 1/2, sorry, the larger triangle has a base of 5, okay, a base of 5 and a height of, calculate our height here, right? This is y equals 4x, where x is equal to 5, so y is equal to 20. Okay. There we go. All right, so a height of 20 and a base of 5. So base is 5, height is 20. And then subtract from that the area of the smaller triangle. That's 1/2 times this base is 3, And what's this height? We evaluate y equals 4x at 3, you get 12. So 3 times 12. All right, so half of 20 is 10, 10 times 5 is 50, half of 12 is 6, 6 times 3 is 18, 50 minus 18 is equal to 32. So I've got that A1, right, back up here, A1 was equal to 24. I've got that A2 is equal to 32. Already we see the answer is going to be correct, as we're going to subtract the first minus the second, 24 minus 32, which gives us our original answer of -8. It's just another way to geometrically interpret this. Okay. And finally, if we want to use a trapezoid, right, just different ways in which we can visualize this is what this is. And in some exercises, you might find one of these methods or another of these methods to be useful. Okay. Interpreting this value A2 as a trapezoid, the area of a trapezoid is 1/2 of the sum of the bases, that is the average of the two bases. And the two bases of a trapezoid are the two lines that are the two sides that are parallel to each other. So in this case, this would be a first base and this would be the second base. Those are the two bases. Okay, those lengths. We take half of the sum of those two bases times the height, and the height is always going to be perpendicular to the bases. Okay, so here's a formula for the trapezoidal area. 1/2 times B1 plus B2 times H. Okay, where in this case we have B1. Okay, I'm going to change my variables here. Let's see. B1 plus B2 times H. Okay, so we don't confuse them with the ones I use for the triangle. So for the trapezoid, B1 is going to be this measure right here. It's this height right here. B2 is going to be this, which I was calling the height of this other triangle. That's what B2 is. Okay, and then H is going to be this distance right here. Okay, so H is this, the height of the trapezoid. So B1 is 12, B2 is 20. B1 is 12, B2 is 20, and then H was equal to 2. It was the distance from 3 to 5. Right, so the trapezoid area, 1/2 times 12 plus 20 times 2. Half of 2 is 1, and then 20 plus 2 is equal to 32. We get the same value as we had here. Okay, so in any case, we go back to the original integral we wanted to evaluate. We take the A1 minus A2, which is going to be 24 for A1 minus 32 for A2. So the original integral I from 3 to 5, 12 minus 4x dx, that's A1 minus A2 equals 24 minus 32, which is equal to -8. Okay. Now, one last thing I want to take a look at here in this section, which is an interpretation. Interpret the definite integral with respect to an application. And the application is distance. So we'll recall from section 5.1 that we said that the area under a velocity curve is interpreted as distance. So if we had let's say we have a velocity function, okay, like so, y equals v of t, okay, if that is a velocity curve, okay. And we already said that if we found the area under here, call that area A or A1, okay, let's just call this A for right now, okay, then A is interpreted as the distance traveled on the interval. Let's put this on the interval from A to B. So let's say this is where x is equal to A, and this is where x is equal to B. All right, so we already established that previously, like we did with rectangles. If the rectangle had a height that was a velocity, and a width that was a time. Okay, there was a time change. This is over the time interval here. Okay, if we multiply velocity times time, we get distance. So we would get a distance traveled. Well, now what happens, though, if we allow our function to go below this axis, below the horizontal axis? Okay, I'll allow it to go out to like here. All right, and then I'll say, let's give a new endpoint value here at C. Okay. And so now I want to include in here, what are we talking about we're finding? If we were to take the integral of this velocity function, not just from A to B, but if we were to take the integral from A to C. Okay, and now so we have A1 right here is the distance that has been traveled on A to B, but then we have A2 right here. Okay. All right, so geometrically, we know that if we take the integral from, let's say, A to C of the function v of t dt, geometrically, we said, well, we can break this up as two area regions, right? We can take the integral from A to B of v of t dt, and that's what A1 was. That was the distance we traveled on A to B, and then, okay, and then we can add to that the integral from B to C v of t dt. What's our interpretation of that second integral, though? Well, the area of that region does tell us about distance. But the fact that it is negative, what does that tell us? Think about the velocities here. For instance, on this subinterval here, the velocity is strictly greater than 0. How do we interpret motion when the velocity is greater than 0 for our object? Suppose this was an object that was moving on a horizontal line. On a horizontal line, that would indicate that the object is moving to the right. So A1 can be interpreted as the distance traveled on AB, the distance traveled to the right or up, okay, in the positive direction. Okay, distance traveled on this time interval A to B, okay, in the positive direction. So imagine there was an object that for this time interval from A to B was moving to the right. It was speeding up until here. This was where it had its maximum velocity, by the way. All right, this right here is its maximum velocity. That's when it was moving the fastest, but it is moving to the right. Okay, so perhaps if I wanted to try to use sort of, vectors to express dynamically how this thing might be traveling along this interval, it starts out where the velocity is equal to 0. So it starts out by standing still. All right, this says the velocity is 0. It does not tell us the position of the object, I might add. It just tells us it happens to be standing still at that time. Standing still, and then it starts moving, so it's moving a little bit slowly, and then it speeds up. So a bigger vector trying to indicate that it's moving faster, and then it gets faster, right? And then ultimately it's at its fastest within this region. Okay, this is where it's moving its fastest, but moving to the right. And then it starts to slow down because the velocity is becoming less and less, ultimately approaching 0 again by here. So it slows down more and more, okay? Right? It's slowing down until it's stopped again, right? So at this point right here, we have the velocity is 0. At this point right here, the velocity is 0. And here we have the velocity is at its maximum. But it's moving to the right along this whole interval. Then what happens once it passes to time B? On this interval here, the velocity is less than 0. Notice, right? The velocity is less than 0 when we are on this interval. What does that mean is happening? If the velocity is negative, it means that the object is moving in the other direction, in the negative direction. If it's moving on a line, it is now turned around and started going back to where it started. Right? So if it's standing still at this moment here, then a moment later it's moving to the left, but only just a little bit because its velocity is very small in magnitude. Right? The speed is small in magnitude. But as it moves through this interval, it gets faster and faster, but it's still moving to the left. All right? And it gets as fast as it's going to go to the left by the time it reaches this point from the look of this curve. So this is the minimum velocity, but it is the greatest in magnitude when the velocity is negative, right there. Okay? So this is where the velocity would be minimum, but that does not mean it's going slow. This means that it is going the fastest it can go in the reverse direction. Right here, the velocity is equal to 0. So the trajectory of this object, the path that this thing has followed, it started from whatever its starting position is, its initial position, which again, we don't know exactly what its initial position was, but it starts at whatever starting position it happened to have. The velocity doesn't tell us that, it just tells us how fast it's going. It moves to the right over this entire interval. So this is at t is equal to a over this interval, and it speeds up and then it slows back down again, okay, until it gets to a standstill at t is equal to b. Then what happens? It turns back around because the velocity becomes negative, and it starts slow at first and it starts speeding up until ultimately we reach the end of the interval at t is equal to c. Now, the distance it traveled to the right is a1. a1 represents that distance it traveled to the right. It is the area under the velocity curve. The distance it traveled to the left then is a2, distance it traveled to the left. The fact that this region is going to be negative is going to be indicative of the fact that it has gone in the opposite direction. So whereas a1 is the distance traveled in the positive direction, okay, then we have also that a2. We have that a2 is going to be the distance the object traveled in the negative direction, is what a2 represents. a2 being distance, meaning non-negative. Okay, so our interpretation then for the entire integral from a to c, it is the sum of the integral from a to b and b to c. Notice this integral from b to c is a negative value. The absolute value of this integral would be interpreted as the area of this region geometrically, which is interpreted as the actual distance it traveled when moving to the left. Okay? The value of this integral from a to c can be found by taking the area a1 and subtracting a2. If a1 is the distance it traveled to the right, or in the positive direction, and a2 is the distance it traveled back into the negative direction, then how do we interpret this difference? The difference a1, where you take a1 was this distance, and then we subtract a2, so the difference between the two would be how far the particle is from the start. And so that's going to be interpreted as displacement. Okay? Displacement over the interval from A to C. All right? It's how far it is at the end of its journey compared to where it was when it started. Okay? If the size of A1 is greater than A2, then it's going to end up to the right of its initial position, right? Because if the magnitude of A1 is larger, then it went farther to the right than it did returning to the left. If the magnitude of A2 is, if it's a greater area here than it is there, if the magnitude of A2 is greater than the magnitude of A1, then it's going to end up farther to the left of the initial position than it started. And if A1 and A2 are equal to each other, that is, if these two areas are exactly the same as each other, then the object is going to end up right back where it started again. Okay? So our interpretation for this integral then is displacement. What if we wanted to find distance traveled? Okay? What if we wanted the total distance traveled over the interval from A to C? How would we calculate that? It would have to be by taking you take the distance it traveled from A to B of our velocity function v of t dt, and you would add to that not the integral here, because remember, this integral is going to calculate as a negative quantity. So we would take the absolute value of the integral from b to c of v of t dt. And how do we know where to split up the original, right, the original interval from a to c? How do we know where to split it to make two intervals out of it? A to b, b to c. How did we find the value of b if we started with an interval from a to c? We can find out by wherever the velocity is equal to 0, right? If the velocity is equal to 0 somewhere between a and c, that somewhere would have to be b. And that's where we're going to then split it up. So we can actually take the absolute value of this integral plus the absolute value of this integral, and we can extend this for as many other integrals as we may have, where the places where we are breaking up into subintervals are always going to be around locations where v is equal to 0, the velocity is equal to 0. So that's how we do it, since v of b is specifically equal to 0. That's how we found out where to split it up. The absolute values on each of these individual integrals are therefore interpreting these answers as strictly distances. What that would look like geometrically, if we take the absolute value of the velocity function itself, it's going to take a reflection of a2 back up over the t-axis, is going to go put that region up here instead. All right, so if we were to try to sketch the absolute value of this velocity function, then what would that look like? All right, so if I wanted y equals the absolute value of v of t for the same function I had up here, kind of had a bell-shaped curve and then came down below here, right? So it would be like from a to b, and then instead of going down like this, it's going to reflect up above the axis here to here, right? So there's a, here's b, here's c, okay? So now we have this region here and this region here, okay? And if we were to add together those two areas, since both of these are now in the non-negative regions, we would get a total distance traveled then. Okay, that's what we would find. And the area of this region is, of course, the same as the area of the region we started with. And the area of this second region is also the same as the area that we started with, right? They both have the same area. Okay, so we can interpret this then as the total distance traveled. So that is the integral from a to c of the absolute value of the velocity function dt, right? Well, then that becomes the distance, okay, the total distance traveled over the closed interval from a to c. So there is an interpretation we can have for the definite integral in general, right? So when it goes negative, and where we can actually interpret a negative output or even a partially negative output from an integral in context for some particular application. And the application we've chosen here is to relate areas under curves to distances traveled. Okay, and this is also related to displacements versus distances, as we had talked about previously in the course. When the velocity is equal to 0, you want to choose where the velocity is equal to 0 in order to create subintervals, right, to test where the object was moving in the positive versus the negative direction, for example. Okay, so that is it for this section. Using your definite integral, can you find the value of an integral by just using the graph where you don't have a symbolic function? This is entirely done in terms of areas. Here's where you might need to use, well, get creative here, areas of triangles, rectangles, maybe even trapezoids. Okay, you might even find more than one approach that you could do to each one of these integrals and see if you can interpret what those have to be equal to through using the graph and geometric reasoning. Okay, so you're going to have to write some Riemann sums. You're going to have to evaluate limits of some Riemann sums. That's when you're using the definition of definite integral. You're going to have to interpret some in terms of areas. Remember that something like an absolute value function, you should graph that function and take a look at the type of the shapes of the regions you get. How do you graph an absolute value function? It is done piecewise, right? We know how to separate that into piecewise pieces. So you should be able to also evaluate integrals of piecewise functions. Try sketching the graph of the function over the interval that's given, and then see if you can evaluate it. This is not telling you how to evaluate, so you can just evaluate it in terms of areas. That's what I would choose to do. But you could also probably do it in terms of Riemann sums. I think you could. Okay, it's up to you. These specifically say areas. I think I would choose areas on this one as well. All right. Let me know if you have any questions when you're working through the homework and anything else for your upcoming exam. This is the last section that will be represented on your next exam. And that's it for now. Take care.